Hello everybody, this is Andy Pilc. It's day 3 of our Dynamic Earth unit, and in this video I'm going to be covering the tectonic plates map that's in your ESRT. I'll cover some quick basic things on how to read it and how to interpret it, and then we'll take a look at a simulation that shows how they actually use earthquake data to make that map and draw those boundaries in between the tectonic plates. So let's just start by looking at the map that's in the ESRT. So on it, you'll see, of course, the plate boundaries, and on the outside bordering the map, we see markers for lines of latitude and longitude. Now, a couple things to note here. First off, let's start with the equator, 0 degrees latitude, and that should look pretty much where we would expect the equator to be, in the middle, meaning that any markers going this way, away from 0, are going to be north latitudes, and any markers moving in this direction are going to be south latitudes. And we have them on both sides just to help make a more accurate reading, right? So here's 10 degrees north latitude, so that 10 and that 10 match. That 20 and that 20 are aligned, and any spot on that point is 20 degrees north latitude, 30 degrees north latitude, and so on. So hopefully that was expected. The one thing that is a little confusing is that as we measure north and south, you need to look to the sides of the map to find those values. Now, lines of longitude are a little bit trickier because it's not the main feature in this map. The main feature is the ring of fire that we see around the Pacific Ocean. So the prime meridian is in a kind of a peculiar spot. It's all the way over here on the right side of the map. And the rest of the spots of lines of longitude, like our international date line, 180 degrees, is all the way over here. All right, so here's 0 and 180 degrees, which is our whole range of lines of longitude, unlike lines of latitude that only go up to 90 degrees. So that makes the east and west longitudes a little bit trickier. So west is, I guess, a little bit easier because if you start at 0 degrees longitude and you move in a western direction, that way, then those numbers should be straightforward until you get to the international date line. So this point right here is 178 degrees west longitude. For eastern longitudes on this map, as we started the prime meridian and move this way, we're starting at 20, we move to 20 degrees east longitude. Now, if you wanted to take your paper and kind of curl it into a cylinder, it might make more sense to do that because 20 degrees is going to continue on the left side of the map and increase in longitude, increase in distance away from that prime meridian until we get to 180 degrees longitude in that direction. So the Mariana Trench, which is home to the Challenger Deep, the deepest trench in the Earth, that would be at approximately, let's see, I can't draw straight lines. Oh, at about 147 degrees east longitude. So that's one tricky thing about reading this map when you're trying to determine the coordinates of hotspots and different plates. But let's take another look at something a little bit different. So we're going to leave this map and we're going to use the Seismic Explorer from the Concord Consortium to take a look at how they actually collected data and drew this map of tectonic plates. So what this simulation is going to allow me to do is show every earthquake that's happened on Earth since they started collecting data in 1980. So let's actually pop this into full screen and let's start up that data. So all of, let's turn volcanoes off for a quick second. So now every single dot that we see is a measured earthquake or a recorded earthquake for the past 41 years. The size of the circle is going to indicate the magnitude, and the color of the circle is going to indicate the depth. And we can use the depth to make an inference about what's happening at that tectonic boundary and give us a hint as to what's happening with the plates. So if we start looking maybe just at the mid-Atlantic ridge over here, we can see that a lot of them are red, meaning a lot of them are happening pretty shallow or pretty close to the surface of the Earth. Now I can also draw a cross section, so I can drag this and we can take a look at that data in a 3D view, point 1 to point 2, and we still again see that a lot of the earthquakes that are being recorded are happening pretty close to the surface, which is where magma is coming out and causing seafloor spreading, which is causing those earthquakes to happen there. If we were to look at one of the region's favorite convergent boundaries, which is right over here, the Peru-Chile Trench, we see that this is a convergent plate boundary, and reading this key, the side that doesn't have the boxes is the subducting plate, and the side with the boxes is the overriding plate, or the plate that's on top. So in this case, the Nazca plate is subducting beneath the South American plate, and here's how they figured that out. So if we go down to where this Peru-Chile Trench is, you're going to see some different colors, unlike before. And if I draw a cross-section of this data, I'm going to start it over here on the Nazca plate, and I'm going to stretch it going inland to South America, which is right underneath the Andes Mountains, and we have some volcanic activity there too. Now, if we throw the 3D view open, here is where we can start to see that subducting plate. So they're shallow over here in the ocean towards Nazca, by the Nazca plate, and as it doesn't really show it too great over here, let's actually get a better 3D view, maybe over here where there seems to be a little bit more variety. Let's take a look here. That looks a little bit better. So now we can start to see the earthquakes being recorded as the Nazca plate is, let's go, subducting beneath the South American plate, right? So here's the top of the plate, and this, if we were to kind of imagine this area over here, this would be the less dense continental South American plate, and the more dense Nazca plate is subducting beneath the South American plate. And then we can take a look at a couple more places in the map. So here's our Ring of Fire. See a lot of tectonic activity over here. You'll see that Marianas Trench, where we were looking at before. So again, we can take a look, at the 3D view. So our Pacific plate is over here. That'd be the Philippines plate, I believe. So this plate, shallow earthquakes over here, and then we can kind of see the subduction of this one plate, which makes sense because over here we'll see the convergence, and according to the key, it looks like the Eurasian plate is overriding and the more dense Pacific plate is subducting. And that's backed up with this view in the earthquake simulator too. So if we were to zoom out a little bit, here we have all the earthquakes being shown. We can also just kind of superimpose some volcanic eruptions, and we're going to see that they also fit into the pattern, right? A lot of volcanoes are happening where we see convergence, especially convergence of oceanic plates, because that's really the fuel that's going to cause rocks to melt and then become less dense and go erupt as volcanoes. We can also show the plate boundaries. And if I wanted to, just to kind of ease up a little bit on some of the data that we're looking at, we can take away some of these earthquakes, and we'll see that the earthquakes and the volcanoes that are on the map are pretty much following the shape of these boundaries as we come to draw them. So now we've looked at how to use this map and a little bit as to how they've made the map. Now hopefully you've learned enough where you can go and solve some of these problems on your own. Hope you found this video helpful, and I'll see you folks next time. Bye.